So today we'll understand and know how to recognize a filter in the shortest possible time. For that we need two important concepts: how impedance of capacitor and impedance of inductor varies with frequency. As you know, in the first case, impedance of capacitor and omega is related by 1 ZC equals to 1 by j omega c. So when you try to plot ZC in the y-axis and omega in the x-axis, what you will get is a hyperbolic graph. That's of course what we expect, because they are related inversely. So what do you see in here? You see that when omega is very short, omega is very low, impedance of the capacitor is very high. So omega tends to 0, ZC is very high, and if impedance is very high, it acts as open circuit. And when omega is very high, then ZC almost equals to 0, or we can say it is very low. And when impedance is low, that branch acts as short circuit. So this is our first concept. Now the second concept, the impedance of the inductor and impedance and just omega angular frequency is related by ZL equals to J omega L. So when you try to plot omega in the x-axis and impedance of inductor in the y-axis, what you get is a straight line with a slope of L. What is the extreme cases here? When omega tends to 0 or omega is very low, the impedance of the inductor is very short. So how it acts when omega tends to 0 or omega is very low? It acts as short circuit. When omega tends to infinity, ZL is very high as it grows linearly, and when impedance is high, that branch acts as open circuit. So these will be our two extreme cases, and these two extreme cases we need to remember: how capacitor behaves when angular frequency is very low, how inductor behaves when angular frequency is very low, and how they behave when angular frequency is very high. Now how can I imply this method? And so suppose, for that, let's take an example of a filter. Suppose here is our input source, here is our capacitor, and here is our resistance, and it is given that our output branch is across the capacitor. So this is our V output and this is V input. Now if you try using transfer function, you will find result, but if you try intuitively, you will get the same result also. How to try intuitively? Look, when input source has very short or very low angular frequency, impedance of the capacitor is very high, so this branch acts as open circuit. When this is open circuit, no current goes or flows through resistance, so at omega tends to 0, V output tends to 0 too. Now when omega is very high or omega tends to infinity, this branch acts as short circuit and no voltage drop is gained across this branch. So all the voltage drop is across the resistor. So when omega tends to infinity, V out is high, and we have seen when omega tends to 0, V out is very low. That is because of these characteristics of capacitance. So what will happen if we try to plot V output over V input, this magnitude with omega? When omega tends to 0, it is very low, so it will start like this, let me use another color. It starts somehow like this, and when omega tends to infinity it is very high and of almost 1. When this is a short circuit, all the voltage of input got across the output, so it's almost 1. And you can intuitively guess in between the graph would be like this. And what is this? This is a high pass filter because it is only allowing the high frequencies. Now suppose I take another circuit simple like this, but just I replace the capacitor with inductor, and it is given that across the resistor is our output branch, and this is our V input, and I want to know what kind of filter am I supposed to get. Now let's draw the plot first. Omega V out over V in magnitude. When omega is 0, Z of L is short and acts as short circuit. So for low values of omega, this is short circuit, so no voltage drop in this branch, and all the voltage drop is across the resistor. So for very short values of omega, you will get almost the gain as 1. This is 1, of course. For high values of omega, what you get is impedance of this branch is very, very high. So this acts as almost as short. When this is short, no current moves through here. So no current is going through the resistor and no voltage drop across resistor. So for high values of omega, this is 0 again. Now how do you complete the graph? Of course, it's like this. You can intuitively guess that. As omega becomes higher and higher, voltage drop across resistor is getting lower and lower. And what kind of filter is this? This is a low pass filter. And what was this we have obtained? This is a high pass filter. Now these are the basic ideas you have to understand and remember. Now let's try a slightly slightly complicated, not too much complicated, but slightly. Third one. Let me give inductor on here. This is inductor, capacitor and resistor. A series RLC circuit. C, L and V input. And it is given that our output is across the resistor. So let's keep on plotting. Now try to see when omega is very low, this is short, this is open, no current going through here, so across the resistor the voltage drop is short. When omega is very, very high, try to see that this is short and this is open. Again, no current going through the resistor because this is open. Inductor is open at high frequency. So for high frequency, you also have no voltage gain, no voltage drop across resistor. These are the extreme cases, and if you know extreme case, you can easily predict what will happen in between. This will be a band pass filter. It won't allow any frequency which is very low, and it also will not allow any frequency which is very, very high. So this is band pass. Now we have seen example of 3. Let's take the 4th one. This circuit only, but I will just change my output. I will plot it here and just like this, and I will say the total capacitor plus inductor branch is my V output branch, and this is of course V input, RCL. Okay. So try to see when omega is very low, capacitor is short and inductor is capacitor is open and inductor is short when very low, for very low frequency of for very low value of omega. As this is short, when omega is very low, all the voltage drop is across the capacitor. So in this branch we'll have all the voltage drop. Sorry, not like this. And omega, when it tends to very high value, this is short, this is open, this is short. For very high value of omega, inductor is open, capacitor is short. Again, no current flowing, so all the voltage drop is across the inductor as it is short, and you can see all the voltage drop is across this branch. And once you have known the extreme cases, you can easily get what will be in between. This is what we call as band stop filter. Why band stop? It is allowing all the frequency except some branch, some band. Except this band, it is allowing all the frequency. That's why it is called as band stop filter. Okay, I'll slightly try to explain few more filters. Let me check if it is clear here. Okay. Suppose this one, if I try to explain. My output branch is across the resistor and also you can say across capacitor, because the same voltage drop will be in here. When omega is very low, this capacitor is short and this capacitor is open. Omega is very low one, and this inductor is short, so current will go through here, and as this is open and this branch does not affect when omega tends to 0. Let me better draw it so that you can understand. Yeah, this is our filter. Yeah, this is our output branch and we have some sort of source here, L, C, R. Okay, when omega is very low, this is open, so this branch does not affect, this is short, so the circuit is kind of like this, if you try to imagine. So all the voltage drop will be across here. Yep. And when omega is very high, this is short, so of course now these two nodes are short because capacitor is short when omega is very high. So you will not get any voltage drop in this node. So what you will be you will have some sort of low pass filter. You can see that you can immediately predict the results once you know how the impedance goes down or up. Let me try another one. Yeah, let me try this one for convenience. Some sort of source here. This is our output branch and this is L, C and R. Okay, try to guess and see when what is happening when omega tends to 0. This is short, this is open, no current going through here because no. When omega tends to 0, this is short, this is open, so this is open and this kind of acts like a short, so current is going in here and the circuit looks kind of like this. This is short, this is open. You can avoid this branch, then what you see, a purely resistive circuit and all the voltage drop is across the resistor. When omega tends to infinity, what happens? This is short but this is open, sorry, this is open but this is short again. So So the circuit diagram looks kind of like this, and you can again see the current will go through here, here and here, and all the voltage drop will be across the resistor. So for both the extreme cases, you get high values of output, and if that happen, we know that is band reject filter. Okay, let me try the last one, this one, for your convenience. L, C, RL, and this is our branch. Okay, again I'm not writing it, but in this x-axis it's omega, and in ordinate this is gain. So when omega tends to 0, how does this circuit look? This is short, this is open. Circuit looks kind of like this. No current will go in here, all the current will go through the resistor, and all the voltage drop is across the resistor. When omega tends to infinity, the circuit diagram is again like this, just that this will be short, this will be open then, and this will be short, and all the voltage drop will be again be across resistor. So this is again another example of band pass filter. Okay, so this will be all the examples. As I said, try out all these examples from your PSpice lab sheet and try to see them intuitively, what happens at the corner frequencies, extreme cases, when omega tends to 0 and when omega tends to infinity. And if you can solve them, it will be all fine to understand how a circuit will behave, whether it will pass low or it will pass high frequencies, very intuitively, without any math, without solving for the transfer functions. Thank you.